All right, I think we're live. Just setting up one last little thing, get my remind up. How's it going? Um, so I hope you guys are having a great spring break. Technically, I don't know if it ended already, but well, tomorrow we have school, so that's very exciting. Um, Hopefully, you get all rested up. The end of the year is in sight, and that's kind of cool, but also a little scary because change is about to happen, right? First of all, hello. Second of all, if you hear a machine in the background, it's because I didn't plan very well ahead of time and I've got a 3D print going on. So you might be hearing my 3D printer in the background, and I apologize about any noise you may or may not be hearing. I don't know. I hear it, but I'm in the same room as it. All right, so we have our Unit 7 test coming up on Wednesday, and I'm guessing it's probably been a little over a week since you maybe thought about it. Many of you, I do know some of you at least, were working on the review guide at some point or another over the week, and if you did, great. If you didn't, that's okay. That's the reason that we're taking the test on Wednesday and not like on Tuesday or something like that, because that way you have some time to get ready and prepare if you get all refreshed and everything like that. Hello. So I believe there's about a 10 or 12 second delay in the streaming thing, so before I can see anything. So if you have a question, just throw it up there, and I might not see it for 10 or 12 seconds. That's okay. I'll answer it. There's a reason I'm doing it live, or almost live, is so that I can answer any questions that you might have that I could show you. Okay. All right. I've talked already for 2 minutes and I haven't even started yet, but I just kind of wanted to set the scene for you. So tomorrow and Tuesday, we're going to do some stuff that will help you get reacquainted with all this, and then Wednesday will be our test. So use Remind, like it says at the bottom. You could ask questions anytime. You could use the chat. You can use Remind. My spring break has been really good. Honestly, my family did not have spring break at the same time, so it was kind of relaxing, restful. I got a lot of stuff done. I know that sounds kind of lame, but it's important to get the stuff done that you need to get done, and I did for the most part. And then, like I said, I have a pretty solid plans, flexible-ish, but pretty solid plans until the rest of the semester, until the rest of the year, which I did just think of something I want to add, and I don't want to forget it. So I'm going to write it down. Let's see. This is how my brain works. Just randomly at the worst times possible, I remember something kind of relatively important. So it does have to do with your class. But anyway, so yeah, it was great. Hopefully you had a good one too. But let's begin. There were two parts of this unit, two standards, if you want to go with that. The first one has to do with just circuits. And the second standard has to do with Ohm's law and solving and all that stuff like that, doing all the math. So this first part, there's not a ton of math, which is, take it. Great question. The PSAT. That's going to be not this coming week, but the following week. Okay, so the PSAT will be not this week, but next week. The date of that, it's going to be either the 11th or the 12th, I believe, for the PSAT. Another great question. We'll talk about all that. Basically, this week we have 3 regular days. We have a SIP day on Thursday, and then we have Friday off for the spring holiday. And then next week, after that, following week, we've got, I believe, Monday and Tuesday are regular classes, and then so I think it's Wednesday, Thursday we have testing. We'll talk more about that all later, So. But yeah, that's good to know. So yeah, this next couple of weeks are kind of weird. That's just kind of how it goes though. So anyway, you say current is the flow of electrons, and for that you would be absolutely correct. So current is the flow of electrons. It's just a definition. So great. Good. So what does a battery do, or any other power supply? What does it provide? Charges, like the electrons, because I just got done saying like the flow of electrons is called current. So does the battery provide those electrons? Does the battery provide the actual flow, the actual current? Does the Does it provide amperage, resistance, voltage, or ohms? It's kind of important. So the answer is a battery. So basically, if you remember all the simulations we did, in this situation, there it is. This is the battery. This is the cell. This is the power supply right there. And if you remember all the simulations that you did, it was a few of them, not like a ton or anything, but those little dots represent the charges. Those little dots represent the electrons that are flowing through the circuit. And the battery actually doesn't provide the charges. Those charges are already there. So this is not the answer. Those charges are already there. The only thing that the battery does, it acts like a pump, and it pumps those charges. And so that pumping action, that causing pressure to push those electrons, is called the voltage. That causes the electric potential difference, that push, the electric potential. So the battery that's like one of those things that is a favorite for test questions. Just the idea, not necessarily worded like this or anything like that, but just knowing that that's what a battery does provide. It just provides the voltage, the push. Okay, the charges are already there. Okay. For electrical current to flow, which of these are necessary? And it's going to be more than one of them. Conductor, amperage, resistance, or voltage. Which of these are necessary for the current to flow? I'll give you a hint, it's two of these. Okay, it's not amperage, because amperage is the name of the flow. Okay, they're all involved. So all of them are involved, okay? But not all of them are absolutely like necessary for current to flow. This is just the name. Amperage is just the name. Resistance is not necessary. In fact, that's one of like the big research projects going around the world, is to get zero resistance if possible. So just to have it flow. But yeah, you need a conductor and you need voltage. You need the push, which is the voltage, and you need a conductor, which is what the charges can flow through, what the current flows through. So you need both of those. My dog is barking now. That's exciting. Should invite her in, but she'd just be a pain. Conductor and voltage, yeah. Wait a minute, who's deleting their answers again? All right, fair enough. Charges per second, that's another definition. What is charge per second? And if you think about it, charge per second just means like if you have a conductor, like a wire here, and you've got those electrons moving through the wire, and they're like moving in some direction, the charge that passes like a certain point, like right here, let's just say, is called current. That's right, you got it. So charge per second. How many charges go by every second? Current. Good. Which of these makes a good insulator? Choose more than one. So an insulator slows down or stops. We'll just say stops. It prevents flow of electrons. So which of these are going to prevent? Now, copper is a fantastic conductor. Okay, this is a conductor. This is the opposite of an insulator. Conductor. That's supposed to be a letter D. It's a conductor. Okay, so that is not one of the answers. Glass and plastic. Good. And rubber. Good. Rubber is good. Gold is another conductor, so that's a bad one. Aluminum is a conductor, so that's another bad. It's a conductor. It's a bad insulator. Glass and plastic are both great insulators because they stop the flow of electron. Okay, they stop current. All right. All right. By the way, I said this. It said at the beginning in like a little text. It's cool if you're just watching and like maybe you got something else going on in the background, or maybe this is the background. But I just want to warn you that that's probably not the most effective use of this. If you're gonna watch this, it's better than nothing to have this on in the background. It's better than nothing to have it on in the background. I'll admit that. But the more you engage with this, the more you pay attention, the more you maybe write notes or whatever, the more you're gonna get out of it, the more you're gonna remember. So just kind of keep that in mind, that this is a tool, and the more you use it, the more you're gonna get out of it. Okay, which wire, if these 4 things were wires, which of them would have the most resistance? Okay, so A is basically a long, skinny wire. Letter B is a long, thick wire. Letter C is a short, skinny wire, and letter D is a short, thick wire. So resistance slows the current. Okay, it slows it down, which means that A will have the most resistance. A long, thin wire will have the most resistance. This will have the least resistance, a short, thick wire. Okay, this is why you don't string, what do you call them? You don't daisy chain extension cords. If you take extension cords and you plug extension cord into an extension cord, you're basically making a much longer wire, and like the wire didn't get any thicker, and so like you can actually cause fires, or cause a short circuit, or cause a fuse or a circuit breaker to break. So be careful. Just don't plug extension cords into another extension cord, because now you're making the wire too long. It's just not meant to handle that much current. Okay, series or parallel. There's only one pathway for the electrons to flow. One pathway. This is like the key phrase to know for this particular one. Yeah, one pathway means series. One pathway. That's like the definition of a series circuit. One pathway. When a new light bulb is added, the other bulbs get dimmer. Series or parallel, or either. So the answer is going to be the one where, I'll just say it, it's also series. Because there's only one pathway, and if everybody has to share the same pathway, then everybody's going to get slower, because now everybody's got to go through the same like resistor, or same light bulb, the same whatever. If everybody's got to go through the same path, then any obstacle in the path is going to slow everybody down. All right. Parallel means there's multiple paths, and so if you add more bulbs in parallel, it's like, hey, we don't have to slow down at all. In fact, we could maybe go a little faster. It doesn't necessarily happen that way, but like we got another path. We're not going to slow down. So yeah, it's parallel, or series for that one. Each resistor has the same voltage as the total voltage. Series or parallel. Okay, this kind of gets into our rules of them. Same voltage is parallel. That's going to come in handy later when we're doing our solving circuits. So same voltage is parallel. I'll just go back. Same voltage is parallel. Same current is series. That'll probably be a question coming up, but voltage is the same, means parallel. Current is the same in a series. When one bulb's out, the others remain on. And I gave you an example of this, I gave you a simulated example of this in class. And you kind of did this with the breadboard too, where you could take one bulb out and the other bulb stays lit. That would be parallel again, because again, you have multiple pathways. And so, yeah, if you take one pathway out, there's still the other path. The current through each resistor is the same. Ooh. All right, cast your minds back a week and a half when we were learning all these rules, right? The current through each resistor is the same in a series circuit. Okay, we'll come back to that. It's going to come in handy again when we talk about solving circuits in those VIRP charts. Series or parallel, this is the last one. You can have a switch that turns off some lights, but not others. In order to have a switch that turns off some lights, but not others, you need more than one path. When you have more than one path, we call that parallel. All right. That's about it. I think there's a few more maybe on your practice, or maybe it's the same ones, I forget. But I brought up these animations in class. I thought they were relatively useful, at least mildly so. They're analogies. They are analogies. They're analogies. Analogies break down at some point, but we're kind of at the beginning of all this, so they're fine, and I hopefully useful to understand what's going on, where this battery, like these charges are at the bottom. When they're at the bottom, they don't have any energy. They don't have any, in this case, gravitational potential energy, GPE, okay? Because they're at the bottom. They're only moving because they're getting pushed by things behind them. And again, it's an analogy, so just kind of bear with me. But then what happens is the battery, increases the GPE, the gravitational potential energy. Or in the case of a battery, it would increase the electric potential energy. And the amount that it increases it is what we call voltage. So now at the top of this little ramp, these charges have gravitational potential energy, which is the analogy that we're using to understand electric potential energy. And because they have this height, they want to fall. They have the ability to fall down or roll down a hill. So they do roll down the hill because they have this energy that lets them move. And by sticking a little windmill or something, a pinwheel or whatever you want to call it, a water mill, a charge mill, a rotor, in there, these moving objects, charges, can cause something to happen. They do work. And so we're able to use the energy that those charges have to cause something else to happen. And this is our resistor, our light bulb, our whatever you want, our heater, whatever. So that's the analogy there. And I wrote all over everything. Eraser. Okay. So I didn't erase everything. So these are the exact animations I showed in class. Here we have circuits wired in parallel. You can see the two pathways. As an electron comes around the corner, it could either go to the left or it could go to the right. And then when it's done, it comes back and both pathways lead to the same path. That's basically what parallel is. So here, if you follow the analogy from before, the electrons are raised up to a higher energy level, gravitational in this case, but it's an analogy for electric potential energy. And same thing, the electrons could either go to the left or to the right. And when they roll down either resistor, they end up at the bottom and they come back and they lost their gravitational potential energy, aka their electric potential energy, or analogy. Okay. And if these don't help you, that's okay. I just erased a bunch of stuff. This is just an analogy. So here's a slightly less busy parallel circuit. I could switch that up for one wired in series, where now those charges have to roll through or go through both resistors. And so you can see how having them wired in series would slow everything down. But it goes down, instead of going down all at once, it just goes down a little, and then it goes down a little bit more for the other resistor. But all right, analogy's done. Oh, no, not analogy's done. This is a combination circuit. Again, it's just an analogy. This may or may not be helpful to you, but you can kind of look at it. I'm not going to really do anything else with that. Okay. By the way, there is a question on your review guide, and it's kind of important to understand this. Why can squirrels and birds and stuff land in high voltage power lines and not die instantly? Well, the answer is, if you're a bird, then you can just literally, here's a bird, ready, look at that. It's got like feathers and tails and, oh, come on. Oh, there's a bird. Hey, it almost looks like a bird. Okay, gotta give it a wing. Oh, look at that. Like, that actually looks like a bird. I'm a physics teacher, I can't draw. But the point is, here, the bird has its like little legs there, and it's got its little legs there. It lands on the power lines, right? And it's got its little toes. They're so like weirdly cute, but you look at them, they're like creepy looking, but they're little bird, little robin things. But they land on that. Now, why don't they get electrocuted? The answer is they're not providing a path for the electrons to go anywhere. Like, they're literally just sitting at the top of the hill of electrons, and if they were to touch like 1 foot on the power line and 1 foot on the ground, well, now they are an off ramp for those electrons. But if they're just standing with both feet on the top, on the high voltage, the high energy, they're not an on-off ramp. They're just standing there, and the electrons are not even going through them, because why would they? There's no reason for the electrons to flow through the bird, because the bird is just standing there. If you were a squirrel or some other animal that decided to, this is going to be a really bad drawing of a squirrel. I don't even know what I just did. This is their legs, I guess. Okay, here's a little fluffy, cute little tail of a squirrel. And then it kind of like is reaching for the ground. So here's, all right, tails usually be longer. So here's its 1 foot, and it's reaching for the ground. And let me draw the head of this cute little squirrel. Oh, what? Holy cow, that almost looks like a squirrel. And now the squirrel is touching the ground. Guess what? Man, that almost looks like a squirrel. Now those electrons are like, hey, I don't have to go through this little resistor here. I could go through this cute little squirrel, and by going through the squirrel dies, because it can't. The squirrel is not designed to handle that much energy going through it. Okay, now the squirrel provided an off ramp for the electrons. Doesn't happen often. It does sometimes, but the little cute little bird is, and so you get the idea. All right, the answer is that the electric potential, the voltage, is the same on both feet. And so there's no pressure causing like the electrons to go through the bird. Okay, in the case of the squirrel, there's a high pressure on the back foot. There's a low pressure on the front foot. So if we stood on a power line, would we die? Don't do this, but no, if you were just to magically appear and you're hanging onto a power line, or you like somehow magically got onto the power line and just stood there, no, you would not die. But here's the problem. You had to step onto that line from somewhere. And chances are you can't just jump and land. And you saw the video I showed you where electricity can arc through the air if you're close enough. So it's that transitional time that really is going to be the dangerous time, where you're either going from somewhere to the power line, like instead of the squirrel reaching down, if you're reaching over to step onto it, or you know what I mean? So don't do it. I mean, they're called linemen, people who work for like the high voltage stuff, they take tremendous precautions to to avoid this. So yeah. So in theory, yes, we could do the same thing, but I mean, we're big old humans, and we kind of lumber around very ungracefully, whereas a cute little bird can just flutter down onto a power line, or a squirrel can just, it takes like, it's like a pound and a half. It's able to leap onto the power lines from the branches. We are not like that. We're just like, I don't know, we're not as graceful as that. So yes, in theory, if we were just to appear there, or we had like high acrobatic skills, we'd be fine. But yeah, don't take that as permission that you should try that, because you will die. Any other questions? I'm glad we had this discussion. Okay. Yes, since we're not I mean, you got the right idea. So in theory, yes, you'd be fine. I just read your second comment. Okay. Now we get into the math. Okay. So here's what it is. You have a graph of voltage versus current. Okay. So you made 3 of these graphs when you measured the current going through the different resistors. And hopefully you got it that in order to find the resistance in a voltage current graph, you have to find the slope. And to find the slope, you basically take, I would just take so what is this point? Let's take something that's actually labeled. So this is somewhat labeled. All right, I kind of like that. Somewhere near the ends is basically a good idea. So 0.2 comma, and I guess we'll call this 0. We'll call it 2.5-ish, 2.4. Okay. On the test, it'll be a lot easier to figure out what it is. So this one is just about 1. I'm not going to do the whole thing. I'm just going to kind of point it out. And then it kind of comes out to about 1.1. We'll call it 1.1. Okay. So then when you plug it into the slope equation, and I can show you how to do slope tomorrow if you want to. I'm not going to belabor this right now, but you use those things to find slope. Here's your x1, y1, and here's your x2, y2. Plug that into the slope equation, and you divide, and you end up finding out the slope is 1.1 ohms. So here's the takeaway that I want you to get. For a V versus I graph, slope is resistance. Okay. For a V versus I graph, for a voltage versus current graph, slope is resistance. Boom, done. You got a question, go. I'm listening. I'm going to put up the next question though while you're typing, and I'm waiting for 12 seconds. I could go back to that one if I need to. So how much current would there be if the voltage was 5 volts? Our voltage here only goes up to 1 volt. So, and while I'm waiting for the question to come up, it's okay, take your time. This is not going to be the right answer. I mean, first see if you can do it. The chances are, that's a weird question. Do we need to use a second point instead of the first point? Oh. Okay. To answer that question, no. Use any point you want. I personally just chose the second point because it lined up with point 2. You could have done this. That looks like probably point 1. And this would be also point 1 or close to it. So yeah, use whatever 2 points you want. And 2 things. If this is a multiple choice test, or if this is a multiple choice question, the choices to choose from, there'll be no question. I'm not sure I understand. Yes, thank you. There'll be no question as to what the answer is. Like, rounding differences won't hurt you on this. And if you're not sure, call me over and we can talk about it. But yeah, choose whatever 2 points you want. I recommend choosing 2 points on the ends. All right. Let me know if that helped or not. Or let me know if that didn't help. All right, so how much current would there be? Now, the current is what we want to find. And if you're ever not sure about like how to find current, always you go back to your equation sheet, and on the second page of the equation sheet on the back, we got our equation right here. Current is voltage divided by resistance. Okay, you might have that memorized by now, but it's right here on the top center of the second page. Current is voltage divided by resistance. So current is voltage divided by resistance. And it says the voltage is 5. So 5 volts divided by the resistance. And if we remember from before, our resistance is 1.1 ohms. 1.1 ohms. And so that means that the current is, well, no, I'm not sure. Let me get my little calculator. Wink. 5. You would think, actually, I do know this one. I have it right now, 4.5. Okay, I did. All right, it's been a while since I've done a live stream. So yeah, the answer is A. Okay, so 4.5. You can also read the graph. However, you might notice that, because you were probably typing your question, but this graph only goes up to 1. Hey, Cody. What's up? So this graph only goes up to 1, which is why this is a kind of a fair question. You know, you have to kind of like combine, know that what I said earlier, slope is resistance. All right, so find the slope. Once you find the slope, you can use that in this equation to find current. Okay. It's tricky because if you were to just kind of guess, you would have gotten this one, maybe, I don't know. But yeah, always double check with the math. Hey, I got an easy one for you. What is I? I mean, hopefully you know this one. Just want to check something. Cool. All right, so just put, you know this. Current is I. I is current. I'm not even gonna, hey, what? Why didn't you go? No. Oh, because I'm asking more questions. Past me was so smart when I made this earlier this week. All right. I'm like, why? I didn't even see that show up. Okay. What is a... Okay, so let me erase what I wrote over here because I remember this is going to be a bunch of them. So the pen is I. Current is I. What is A? Well, A is amps. So that's also current. Okay, so I is the symbol for current. A is amps. That's the unit of current. Hang on. Yeah. What is V? It's not exactly super hard, right? V is voltage. Honestly, feel good about these types of questions. If you know these and these are sort of insultingly easy, it's still good to review it. Please do, because you don't want to second guess yourself. R, resistance. Like the first thing on the review guide, I think. What is P? Oh, power. Ooh, what's, okay, this is omega. This is our little friend omega. It's Greek letter. And that is the unit of resistance. Okay, resistance. By the way, if you weren't here at the beginning, if you hear my 3D printer in the background, I apologize. Poor planning on my part. Poor planning on my part. Like, I'm going to print this thing. It's going to take 12 hours. I better get it done at the end of spring break. Yeah, I forgot about the live stream review. You might not even hear it, so maybe it's just me. All right. What is W? W stands for watts. Watts. That is the unit of power. Okay? Just like A is amps is the unit of current. Okay? That's about all of those. Let me know if you got questions. I say I'm checking my phone, but it just went into sleep mode. Okay, nothing. How to solve for current? That's almost a question. Blah, blah, blah. You're not sure? Guess what you do? You pull out that equation sheet. Even if you're 85% sure. Oops. You pull out the equation sheet. Current is V divided by R. Okay, you could check that on your equation sheet, and you should. So current, they're not all the same. They're not all the same. V divided by R. Okay, these are definitely not the same. You know, any algebra, you know they're not the same. All right, you got a pool filter motor. It's rated for 1,119 watts. And it draws 5.1 amps of current. How much voltage is required? Okay, so let's just figure some stuff out. Watts is power. Amps, you know this, right? Current. And power is capital P, current is capital I. We do our little P is 1,119 watts. We've got I is equal to 5.1 amps, and we want to know voltage. Okay. How do we do that? That's what we were given, right? So we go to our handy dandy equation sheet. Maybe, there it is. And we see, oh, it's right here. P equals I times V. Those are the three that I've got. Those are the three I got. I'm interested in one of the three, but those are the three I got. So I'm going to use that equation. And I'm going to say, all right, okay, cool. P equals I times V. That's from the equation sheet, but I want V, which means I need to divide both sides by I. So V is P divided by I, which was just barely hanging on to its bottom there. V then is 1,119 watts divided by 5.1 amps. And when you put that all together, you get 220, well, volts. Okay. I said it in class, the units do work out because all of these units are basically made up of a bunch of other smaller units. And yes, okay, good. So if you put it in the calculator, you're going to get 219.4. I mean, I saw that. I think that's important. And so on a multiple choice question, it might not have your exact answer, So you should choose the one that's closest. Okay, so 220 volts. So there you go. That's how much voltage it would, which means that if you plug your well, it would have a special plug. It would have the I'm not gonna get into it. There's like a special plug for 220 volts in the United States. Yeah, you would know it if you saw it. It looked, well, maybe you wouldn't, but you would know it's not the kind you could plug into a regular outlet. All right. Here we go. Now, I wrote it on the board. I should put a picture. Maybe I'll write it up on the board again tomorrow and Tuesday, but not Wednesday. The voltage across the 15 ohm. Okay, you're going to see a question like this, and you're going to wish that you could just answer this question and not do everything else. And I wish I could tell you that that was true, but it's not. You might not have to do every single little thing, but you can't just solve for it. You can't just plug it into some equation. You got to do the verb thing. So you actually have to make the table. So the total for verb, and yes, I just enjoy saying verb all the time. It's physics. We got 1, so I1, R1, and P1, V for 2. And by the way, this is like, 1, 2, 3. I'm just gonna go clockwise. You go in whatever order you want to go in, but that's pretty much what I do. And also, you should probably focus when you're doing it, because trying to talk at the same time. So P2. Well, I'm not leaving myself like much room for. So take this as an example too. I don't know what I'm gonna have to do here. I'm just gonna keep going. I'm gonna regret it though, because I didn't leave myself room to write the actual answers. Okay, so there's my boxes, such as they are. We'll see how I could do here. I feel a sneeze coming on, so I apologize if I sneeze. All right, I'm gonna actually try to draw this. This is something where if you have a school ID, it's nice and helpful to draw straight lines. I actually might have room now. You don't even have to draw the lines. It just helps me, like, do what you want to do. So I'm pulling up a picture of the what I wrote on the board the other day before we left for break, so that I'm consistent with what I've already said, right? So I'm gonna just basically, it's hard to see it, but this is, yeah, I'll just write it. Okay, so there's these rules. In a series circuit, there's one path. Okay. In a parallel circuit, there's multiple paths. That's a T. Multiple pathways. That's a 1 path. Okay, I knew something looked wrong. In series, when things are wired in series, the current is the same everywhere. In everything that's wired in series. In a parallel, V voltage is the same through whatever's wired in parallel. In a series circuit, V adds up to the total. But in a parallel circuit, the currents adds up to the total. And again, I'll write these a little bit more clearly on the board where I have a little bit more room. To find the total resistance equals R1 plus R2 plus whatever other resistors there are. To find the total resistance in parallel, you have to take the inverse of the resistors. Okay, and then you have to take the inverse of that answer. All right, that's the rules for circuits to follow. And On top of that, I do highly suggest that you write the equations. V equals I times R. So that's not the one on the equation sheet is, I don't know what I was just about to write here because I'm talking while I write. This is the one on the equation sheet. I equals V over R. That's the equation sheet version. And then the one that I don't think we use very much is the resistance one is V over I. I mean, it doesn't hurt to have it on there. And then you want P is I times V. So I just, like, P equals I times V is on the equation sheet, of course. And then the middle one at the top is on the equation sheet. But I like to have all of them on there just so, on your scratch paper. So you don't have to keep referencing it and keep figuring out everything. Okay. So there we go. Keeping all those rules in mind. And if you can't read my writing, I apologize. Just let me know. I'll try to fix it here. But like I said, I'll also mention it in class. Keeping those rules in mind, we're going to solve these. I'm going to switch to a different color because that way at least maybe it could be somewhat clear. So actually I'm going to use a bunch of different colors. So I apologize looking over to the other monitor because that's where, okay. All right. So I'm going to start with the givens. The total is whatever's happening at the battery. All right. Like I said, some people call it like naught. They call it something else. It's okay. They're both fine. So this is going to be our 9 volts. Our resistor 1 is going to be 5 ohms. Our resistor 2 is going to be 10 ohms. And our resistor 3 will be 15 ohms. Okay. So that is what's given. So I'm going to switch colors because why not? And now I'm going to look for what I call easies. Easies are, that's my word for these things. Okay. For anything that follows these rules, you don't have to write this word down. I'm just trying to explain where I get this word from. Because I don't have to do any math is what it comes down to. Except for, I guess, the total resistance. But it follows these rules. And right now I can't do any easies. What I call easies. So I'm going to switch colors, I guess, to, let's go to this. Let's see how green looks. I'm going to do some math here. And so basically what I'm going to do, the first thing you want to try to do is find total resistance. If you can find total resistance, usually you can because you usually know the resistors. And if you know the resistors, just see if they're wired in series or parallel, then you could add them all up or do the inverse thing if you need to. So in this case, this is in parallel, this is in series. And so since it's in series, we could just add up these resistors. So 5 plus 10 plus 15 is 30 ohms, okay? So 30 ohms of resistance. That's the total. So we haven't gotten our answer yet. We want to know the resistance across a 15 ohm resistor. All right. Wait, we want to know the voltage across the 15 ohm resistor. So as soon as we get this voltage right here, we could stop. Unless you want to keep going to make sure the math works. Because if you keep going and you find out the math doesn't work, then you know you did something wrong. But let's not. Okay, now that we've got our 30 ohms of resistance total, we now have 2 of the 3. And so now we can use our equation, our middle equation, to solve for total resistance, total current. Total current is going to be that V divided by R. So let's see, current is going to be 9 volts divided by 30 ohms. Okay. I can't quite do that in my head, so I'm going to pull up my handy dandy calculator. And so 9 divided by 30 is 0.3. So my total resistance is 0.3 amps. Now, that's kind of cool because that's an easy. In a series circuit, the current is the same. Not Siri, go away. My phone likes it when I say the word series. So anyway, so now I know that if that's 0.3, then that means this is 0.3 amps. And that means this is 0.3 amps. And this is 0.3 amps. Okay, so because that's just how it goes. Let me just draw that really quick just to make sure we're clear. So that means if we have 0.3 amps coming out of the battery, because remember, current is the flow of electrons. That means that same amount of current is going to go through that resistor. That same amount of current is going to come around the corner and go through that resistor. It's going to go around the corner and go through that resistor, and then it's going to end up back at the battery, and it's going to be 0.3 amps everywhere because it never split up, and it's always going to be that total. So that's why the current is the same everywhere in a series. All right. Now, hey, look, we're almost done. We've got, because we're trying to solve one specific question, we could just figure out this last one, V equals I times R. So if I take my, and by the way, if you can't see this green, let me know. Hopefully I shouldn't use this green, I guess, but I'm stuck with it for this one right now. So V equals I times R. So I'm going to take my current, which is 0.3. I'm going to multiply that by the resistance, which is 15. And it turns out my answer is going to be 4.5 volts. I'm done. I'm done. If I want to go further and I want to complete it, I can make sure that that all the math works out. And if you have extra time, you definitely should. But if you are trying to keep things moving on the test, maybe just flag it and come back later and check it. But you have an answer, and I would definitely come back and check it if time allows. But for now, I'm going to move on. Questions, let me know. Okay. So now we have another circuit. This one's in parallel because there's multiple paths. So in this case, I'm going to switch to the red again so I'm consistent. Whatever current comes out of this battery, whatever it might be, some of it's going to go this way. It's going to split up. Some of it's going to continue on and go this way. And some of it is going to continue and go this way. And then that current is going to come this way. It's going to join up with whatever current's coming out of there. They're going to merge together and rejoin. And they're going to go together and they're going to merge together with the current that went through here. And they're going to basically recombine and go through the, I switched sides, but whatever. That's going to be the current. Do I have to draw the whole thing? What is the current going through? I do. I gotta do that whole table again. All right. But I'm not sure what I just did. All right. Ooh, I switched to highlighter. That's what I did. Pen. All right. So I do have to do the whole thing again. And yeah, we just switch colors. So, I mean, there's no getting around it. So the sooner you just like admit you got to do it, VIRP for total. But as you saw, you might not have to do all of it. And definitely don't talk while you're doing it, because then you'd be talking during a test. But you might mess it up like I am. R1, P1. Let's just go down the line, 2 and 3. There, now I'm less likely to mess it up. 2, 3, R2, R3, and P2 and P3. P is nice if you do have time to go all the way to the end and solve it, because then the powers should always add up to the total. Okay. When you get to the more complicated circuits, hopefully you remember that sometimes the others don't always add up to whatever the column they're in, but power always adds up. It's like, man, I wish power was in my class because I forgot how amazing a person that person is. That's my joke about power being the one friend that doesn't hang out with VI and R. Okay. So here's how we do it. What color did I use last time? It doesn't really matter, but all right, purple. All right. So I'm going to start with what I know. What's given? The battery says 9 volts. Resistor 1, same resistors, but they're in a different order, I guess. Let's go from left to right. 5 ohms and 10 ohms. Okay, now, first thing you should do, find total resistance, if possible. And I'm going to switch to blue. To do that, this is a This is a resistor that's in parallel. So what I need to do is add up the inverses of those resistors. So 15, and then I'm going to hit the little, on my calculator, it's right here. It's a little x to the -1 button. So I'm going to hit that button right there, okay? I can show you where that's at on your calculator. Plus 5 inverse plus 10 inverse. Okay, you could also do like 1/15 plus 1/5 plus 1/10, and then you take 1 over that answer. I just prefer the inverse button. So don't forget to, this part, everybody forgets it once, or at least once. It happens, okay? So don't forget to take the inverse of the answer. So the resistance, the total resistance is gonna be 2.7 ohms. 2.7 ohms is my total resistance. And look, we're kind of in the similar spot as we were last time, where now we can actually figure out that total current. And so that's the next thing we're gonna do. I switched to blue, okay. So, oh, well, good. So blue it is. So now we have total resistance, total voltage. I'm going to figure out the current, the total current. I equals, where is it at? The middle one, V over R. Okay, so I'm going to take 9 divided by 2.7. When I do that, 9 divided by 2.7, I get 3.33333. All right, I didn't think I needed to bring up the calculator to show you division, so you can take my word for it, or you could check. Okay, so 9 divided by, actually, let's just double check because I don't want to steer you wrong here. 9 divided by 2.7, voltage divided by, yeah. So 3.3333, good. Now, why is that important? I don't know if it was necessary because we forgot about, or I forgot about one of the easies. I just like to find total voltage first, or total resistance first, if at all possible. But one thing I could have done right away is these are all wired in parallel. And the thing is, if you have things in parallel, they have the same voltage. So everything is the same voltage. And it turns out I didn't even need to do the first one. That's correct, but I didn't need to do it because all I need is the 15 ohm resistor. And that means I could have, knowing the voltage is 9 volts, I could have immediately solved for that. I could have saved myself like seconds and done it right away. As soon as I got 9 volts and I had the 15 ohms, I could have done 9 divided by 15. Let's get my calculator up again. So 9 divided by 15, the voltage divided by the resistance, and my answer for the test question would have been 0.6 amps. Okay, and that's my answer for the question. Do you have to go on? You don't have to, but if you have time, maybe like put it as the answer, especially if it's a choice. If that's an option, that's a good sign you got it correct. Okay, but you don't have to go on after that because it seems like you got the answer. You have some pretty good feelings about it. You're pretty. It seems pretty reliable. But flag it and come back to it if you have time at the end. All right. All right. I've got one more question. You know what it's going to be too. I bet. I think I got one more question. Yeah, this is it. Okay. I told you there's going to be a question like this on the test, right? You're going to have to do a combination circuit, and that's okay. You still approach it the same way. It's just they're not as cut and dry as some of the others. I'm going to make, they're labeled. See, R1, R2, R3, R4. So that's kind of neat. So I'm just going to do what I got to do here. You know, I'm not going to complain. VT, IT, RT. And if I have time to check later, I'm going to use the power to check. So I've got 5 resistors. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1. And yeah, it takes some time to do it. But you know what? Just do it. Just do it. No use complaining. Now, should you save this question for last? Probably. 1, 1. Because it's going to take a good chunk of time. And unless it's an FRQ, If it's multiple choice, here, let's just do this, 4, 5. If it's multiple choice, it's worth one question, 1 point. 4, 5, 3, 4, 5. It takes time. What can I tell you? You know that. I know that. All right. I'm gonna try experiment here without like drawing the lines. No, you know what? If I don't, I'm just gonna like hate myself because it's gonna look all unorganized. And the whole purpose of tonight is to be as clear as possible for you. And so I'm going to try to do that. So bear with me while I draw lines on the screen. Why did I not do this ahead of time? Because I want to show you that real time, how long it takes. Like, I want to be realistic with you here. You're not going to get grids provided for you for your test. Okay. So it does take a few minutes. I did consider putting these on my screen ahead of time, but then I'm like, no, because that's not fair to you guys. You're not going to get it. You hopefully will have you'll have had opportunity for tons of practice prior to the test. So, what was I using for the givens? Purple, right? So, just draw them. It's okay. So the total voltage is 50 volts. I want to know the total resistance. So I'm going to have to do that. Then the current going through R4. So where's R4? I want this box. And I want the total resistance. Those are the two goals I'm shooting for, right? Okay. R1 is 20 ohms. R2 is 15 ohms. R3 is 10. R4 is 5 ohms. I do recommend writing down the units like that. Okay, just to remind you, just to kind of remind yourself, are you doing it correctly? Because it's like a little mini check for your brain and for your fingers to make. Cause sometimes it's like do 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 do, and you might get messed up there. All right, now here's the problem. We can't just add all these voltages up, and we can't just do the inverse thing for them straight up, because as you undoubtedly know, these three are wired in parallel, but then we have these other two wired in series with each other and with this whole chunk of parallel. So the whole trick here, and there's a whole video or two of me explaining it. Actually, there's 2 videos on my YouTube channel. I'm going to also explain it right now, but if you want like maybe a slightly slower, this is like the crash course review day, right? But I'm going to remind you right now. I'm going to walk through it, but maybe rewind later or something, or ask me. But basically what I'm going to do is I'm going to work these out from the inside out. I'm going to go from the inside out. Overall, it looks like we could kind of call this a series circuit. It's kind of like that with a parallel circuit built inside of it. All right. Maybe that's not the best way to do it, but it's one way to do it. Okay. You have a parallel circuit embedded within a series circuit. So I'm going to see if I could solve the resistance, not you, Siri. I'm going to see if I could solve the resistance for this parallel circuit first. All right. So let's do that. I'm going to use this blue color. They're in parallel. So I have to basically take the 15, the 10, and the 5. And I need to do the inverse thing for those. So I'm going to do 15 inverse plus 10 inverse plus 5 inverse. And when I do that, you'll know because I'm going to do it right in front of you. 15 inverse plus 10 inverse plus 5 inverse. Okay, I get that. Cool. Wait, we got to remember, take the inverse of the answer. So my total resistance for that is, I take the inverse of that answer, 2.73. This looks familiar. Oh yeah, because we did just do, not this exact problem, but we did something similar. We just did 15, 10, and 5 in the previous question. Right here. That's why we got that. So that is the total resistance for that. Where am I at? There we are. So 2.73. Like, Mr. Jern, why'd you put the 3 there? Do you need to? No. But I try not to round I try to avoid rounding as much as possible until the very end. So I added a little bit extra there. It just gonna, I don't know. It just, yeah, there's that. So what that means is this chunk of resistors here acts as a 2.7 ohm resistor. So like it's called the equivalent resistance. So the equivalent resistance of those three resistors wired in parallel is 2.73 ohms. Okay. Now, whoa, my whole house just creaked. I don't know, is it windy out? So now what happens is, where's my pen? Oh, there we are. Whatever current is going to go through this resistor is going to go through it, and then it's going to come here and it's going to split up. Some of it's going to go this way, some of it's going to go this way, some of it's going to go this way. And when it's all said and done, they're going to all come back together and join back up and go through this resistor here and then back around, right? So the question is, how much resistance goes through there? I'm sorry, how much current goes through there? How much current goes through there? And the big question is, how much current goes through that one right there? But we're taking all three of those as one big lump of resistor. And we're going to say, all right, the total resistance for those three together is 2.7 ohms of resistance. So now we could take that 2.7, add it to the 25, add it to the 20. So we get 40. So 20 plus 25 is 45, plus 2.7 more, so 45, 7.73 ohms. Okay, that's my total resistance. And that's one of the questions I was asking about. All right. So if you just missed that, like what happened? You just got an answer. Yeah, I got an answer. Why? How did I get that answer? All right. I figured out that the total resistance of these three together is 2.73 ohms. Okay, these three resistors together as a group are wired in series with this 20 ohm resistor and this 25 ohm resistor. So if you look at these as a group, these three as a group, that's how they're wired in series. So when they're wired in series, you can just add them up. So 20 plus 2.73 plus 25 gives me 47.73. Got my total resistance. Now, that doesn't help me figure out, well, it does, but it doesn't directly help me figure out the second answer, the second question. What's the total current? What's the current going through R4? So for that, I need to do a little math. So let's do that. So now that I've got the total voltage and I've got the total resistance, I can figure out the current. Going back to my equations, I equals, just to make sure, I'm going to go back to make sure, V over R. So V over R. So I'm going to take 50 volts divided by 47.73 ohms. And that's going to give me my total current. So let's do that. So whenever I have two of the three, I could just do that math. So 50 divided by 2.7. Whoa. All right, 47.73. So I got 1.04, I guess, 1.05. All right, I don't want to just write 1. Seems wrong, so I'm going to write like that because I don't want it just to be 1. I feel like that's weird. So there we go. So my current is 1. My total current is 1. That means that coming out of the battery is 1 amp of current, 1.05 amps of current. Okay, so I can write that down here if I want to. 1.05 amps. Okay, same thing down here. So that means going through this resistor. Oh, so going through this resistor is 1.05 amps. I'm going to write that down right here. 1.05 amps. And then that 1.05 amps gets split up 3 ways. I'm not sure yet how. And then it all comes back together and it goes through this resistor, 1.05 amps. So for the R5, I could write 1.05 amps. That's so close to the one I want, but it's not the one I want. Okay, so now what? Okay, I wish I could just get the answer for I4, but I can't. So I'm gonna get what I can get, and I now have 2 of the 3 for a couple of these. And let me just switch back to some other color. Let's go with purple. I know purple's given. I don't want to least I want to be a little consistent. What haven't I used? I guess I'm using blue. So now I have 2 of the 3 for these two. And so V equals I times R. So if I take V equals I times R, so I'll take 1 point, get my calculator out. So if I take 1.05 times 20, the voltage here is 21. It's strange, but that's what it is, I guess. And if I do the same thing down here, 1.05 times 25. Oh, see, that's a nice, okay, that's decimals. That's what I expect. 26.25 volts. All right, cool. So I got more voltages. I got some voltages. Great. So what does that get us? Well, okay, let's think this through a little bit. That means that I started out with a plus 50. All right. I lost going from here to here 21 volts, and going from let's go, I guess we're gonna go right over that. Going from here to here, I lost another 26.25 volts. Okay, what that means is, where can I squeeze this? If I take 50 volts minus 21 volts minus 26.25 volts, then that's going to tell me how many volts it is from here to here. All right. So let's just do that. Just got to do subtraction, which means, where's my calculator? There it is. All right. It's getting a little fuzzy. All right. So 50 minus 21 minus 26.25, 2.75. Okay. I'll write that down. 2.75 volts. Not a lot. It's not a lot. That's okay. 2.75 volts. Okay, so now we know, and these are wired in parallel. So parallel, they're all going to have the same voltage. So this is negative 2.75 volts. So going from here to here, all 3 of these resistors are going to have 2.75 volts. Because they're all in parallel. And now we have 2 of the 3. So what we got to do, it's better be an FRQ, right? Oops, doing the wrong thing. Because you want to get as much credit as possible for this. Where we go. Okay, V equals I times R. So 2.75. Hang on. I equals V over R. So I got the voltage, 2.75, divided by the R, which is resistance. That tells me that the current going through here is 0.55 amps. Okay. Cool. Let's just make sure. That's our answer, probably if it's multiple choice. If it's an FRQ though, let's just continue this. So let's figure out these other 3 and see if they add up to 1.05. So this one here is going to be 2.75 divided by 10. 10. Where we go? So it's going to be 0.275 amps. And this last one will be 2.75 divided by 15. This doesn't work. I'm a little scared, honestly. Okay, so I take 0.183 plus 0.275. Nope. Okay, fine. Plus 0.55. Close enough. Okay, it's not 1.05, but we're getting into like really small numbers here. It's close enough. We're good. We're good. We're good. Okay, but we're good. And if you really have a lot of extra time, you can figure out power and just double check that it's the correct answer. All right, there you have it. Any questions for me? You'll stick with it? An hour and 10 minutes. All right. Very good. I'll just put this back up just for funsies. And all I'll just say is do the review guide. Ask me questions. We're probably going to have like a little... I'll have something for you tomorrow that'll test how you're doing with all this. But do the review guide, circle the questions that you don't understand or that you want to ask questions of or that you need to just work through. And study. Okay? You can prepare. You can do this. It's not going to be that bad. All right. Seeing no questions, I guess I'll call it a night then. All right, you all have a fantastic evening. Enjoy the last couple hours of your spring break. I will see you tomorrow, and it'll be amazing. All right, have a good one. Bye.